In last video, we have discussed four standard forms for non-linear partial differential equation. The four standard forms are function of PQ equal to 0, function of ZPQ equal to 0, function of XP equal to function of YQ, and the last is Z is equals to PX plus QY plus function of PQ. Now today we discuss general method for finding the complete solution of partial differential equation, that is Charpit's method. It is very important for exam point of view that the partial differential equation is function of x, y, z, pq equal to 0, where z is dependent variable and x, y are independent variable. We just find 5 partial derivatives: del f upon del p, del f upon del q, del f upon del x, del f upon del y, and del f upon del z. And the auxiliary equation, that is also known as Charpit auxiliary equation, is given by dx upon minus del f upon del p equals to dy minus del f upon del q equal to dz upon minus p del f upon del p minus q del f upon del q, that is equal to dp upon del f by del x plus p del f upon del z equals to dq upon del f upon del y plus q del f upon del z equals to del f upon 0. So this complete equation is known as Charpit auxiliary equation. Now here we take the terms whose integral are easily calculated so that it may easier to solve for p or q. We just substitute all the derivatives in Charpit equation and we solve it, and then we take two easiest terms and solve either for p or either for q, and we find a relation, and this relation is used in equation 1, and by these two equations we find the value of p and q, and this p and q is used in dz equal to p dx plus q dy, and when we integrate this term we get the solution by Charpit's method. Let's see the example. Solve px plus qy equals to pq by Charpit's method. So first we take all the terms to one side, either left side or right side, and make it is equal to 0. So px plus qy minus pq is equal to 0. Now what we have to find? We have to find 5 partial derivatives. So del f by del x. Just partially differentiate equation 1 with respect to x. We get only p. Del f upon del y, that is q, and del f upon del z is 0 because there is no z. Del f upon del p, that is x minus q, and del f upon del q is y minus p. So now we have 5 partial derivatives. Now use Charpit's equation and substitute all these partial derivatives in Charpit's equation. So when we substitute all these values, we get dx upon minus x minus q, dy is minus y minus p, dz is minus p, del f upon del p is x minus q, and minus q, del f upon del q substituted by y minus p, dp upon p equal to dq upon q equal to df by 0. So here we see the very easiest two terms are dp upon p equal to dq upon q. So let's choose these two terms, dp by p equal to dq by q. By integrating dp upon p equals to dq upon q, we get log p is equals to log q plus log a. Log a is integrating constant. By using the property of log, we get p is equal to aq. Now use p is equal to aq in equation number 1. We get q a x plus y equals to a q square. Now again simplifying, we get q is equals to y plus ax upon a. Now using this value of q in p equal to aq, we get p is equals to y plus ax. So we have two terms p and q. Now using p and q in dz equal to p dx plus q dy, we have dz equals to y plus ax dx plus y plus ax upon a dy. Taking y plus ax as common term and taking LCM of a and multiply it to left hand side, we get a dz y plus ax a dx plus dy. When we integrate this term, we get az equals to y plus ax whole square upon 2 plus b. So this is the solution by Chapit's method. Now we have another example, pxy plus pq plus qy equals to yz. Now take all the terms to left hand side and equate it equals to 0. Now we have auxiliary equation dp upon del f by del x plus p del f by del z equal to dq del f upon del y plus q del f upon del z equal to dz upon minus p del f upon del b minus q del f upon del q equals to dx upon minus del f upon del p equals to dy upon minus del f upon del q. So first we find all the partial derivatives, del f by del x, del f by del y, del f by del z, del f by del p and del f by del q, and substitute all the values in Chapit's equation. So we have dp upon 0, dq upon px plus q plus qp equal to dz upon minus p xy plus q minus q p plus y equal to dx upon minus xy plus q equal to dy upon minus p plus y. So here the simplest term is dp by 0. So we take first and second term. So dp by 0 gives dp equal to 0, and when we integrate we get p is equal to a. Use this p is equal to a in equation number 1 and we get axy plus aq plus qy equal to yz. After some simplification we get q is equal to y z minus ax upon a plus y. So now we have two terms p and q, and we use p and q in dz equal to p dx plus q dy. We have dz is equals to a dx plus y z minus ax upon a plus y dy. So we just take a dx to left hand side, we get dz minus a dx, and z minus ax to again left side in denominator. So we get dz minus a dx upon z minus ax equal to y dy upon a plus y. Now in right hand side we add plus a and minus a. We have y plus a minus a upon a plus y dy. Again simplifying we get dz minus a dx upon z minus ax equal to 1 minus a upon a plus y dy. So when we integrate this term we get log z minus ax equal to y minus a log a plus y plus b. So this is the solution by Chapet's method. Now again we have a equation p square plus q square y equal to qz, and we have to solve it by Chapet method. So again we take all the terms to left hand side, and we have p square plus q square y minus qz equal to 0. Again we find 5 partial derivatives, del f by del x, that is equal to 0. Del f by del y equals to p square plus q square. Del f by del z is minus q. Del f by del p, that is 2py. Del f by del q is 2qy minus z. Now again use these 5 partial derivatives in Chapet's equation. We have dx upon minus 2py equals to dy upon minus 2q plus z equal to dz upon minus 2p square y minus 2q square y plus qz equal to dp upon minus pq equal to dq upon p square plus q square minus q square equal to df upon 0. Now here we choose dp and dq. Then we have dp upon minus pq equal to dq upon p square. When we simplify, we get dp upon minus q equal to dq upon p, and by cross multiplying we get p dp plus q dq equal to 0. When we integrate this term, we get p square by 2 plus q square by 2 and equal to some constant, and we multiply 2 to right hand side, we get p square plus q square, and let the new constant is a square. So here we have a relation p square plus q square equals to a square, and we use this relation in equation number 1. When we replace p square plus q square by a square, we get a square y equal to qz, and we find q is equal to a square y upon z. Now we substitute this value of q in p. We get p is equals to under the root a square minus a raised to 4y square upon z square. So when we simplify this term, we get p equal to a by z under the root z square minus a square y square. Now we have both values p and q. Now use the value of p and q in dz equal to p dx plus q dy. We get dz is equals to a upon z under the root z square minus a square y square dx plus a square y upon z dy. Rearranging the terms, we get z dz minus a square y dy upon under the root z square minus a square y square equal to a dx. Now after integration, we get z square minus a square y square equals to ax plus b whole square, and this is final solution which we get by Chapet's method. That's all.